All right. Well, thank you very much. It's a great pleasure to be here. Thanks for spending your precious Saturday here and to listen to a few ideas and looking forward to discussions during the day. So I want to talk about code quality as the first talk. So 12 ways to make code suck less. So how did I figure out 12 ways? Simple. I just said I want 12 ways and I looked for 12 things. So just a random number, really. But it turned out that these are things that we see quite often. Some of this you have encountered quite often. Some of that maybe would help us to think a little deeper and maybe change some of the practices. But I want to start with a question. Usually there are about maybe 3, if not 4 types of people. There are the why kind of people. They keep asking you the question why all the time. Why are we doing this? Why should we do this? There are the what kind of people, like what are you doing? Like usually managers, like what are you doing? How kind of people. These are the most troublesome people. How do you do this? How do you do this? They want to know all the details. I'm more of the why kind of a person. I always want to know why. Do we need to do this or not? So why is a very important question for me. I'm more of a why kind of a person myself. So why should we really care about code quality? And I'm going to say probably the number one reason to do this is you cannot be agile if your code sucks. As simple as that. If you're sitting down in a meeting and they're telling you that we need to implement a certain feature or make a change to existing software or make an enhancement, and when they're talking about it, you realize, oh wait, to do this, we got to touch that XYZ module, and the last time I touched it, I couldn't go home for the weekend. I'm going to convince them this is not what we want to work on. So it's incredibly difficult to be agile if the code that we work with is of not good quality. So code is how we tell our colleagues how we feel about them. Do you tell your colleagues, I love you all? Or do you tell your colleagues, I hate you all? It is how we actually tell them how we feel about it. Because code is written, but it's rewritten and read many, many, many times. It's a little strange that a lot of times we try to really care about how to write code when we should really be caring about how to read code. Because we only write it once, but we rewrite it and read it many, many times. So the quality of code is extremely important from the point of view of how to maintain this code. The first law of programming says low quality lengthens the development time. So if you really want to slow down in maintaining the code, you want to really create poor quality code because it drastically slows down ability to continue to develop the software. So quality again has a very big impact. But what is quality? And that's where the real trick is. We all can agree, and I'm sure everybody that you come across, you ask them, is it important to develop good quality code? Everyone will say yes. But the problem is not in agreeing that we want quality. The problem is agreeing what that quality really is. I once worked with a guy who had a very weird definition of quality. He said this code is great because I wrote it. I don't think we want to have such measures, right? So we need to be able to really tell the code is of good quality. How do you really measure quality? And that's not really easy to say. There's no one definition. Here's my definition. And what I would like to say is the quality of code is inversely proportional to the amount of time and effort it takes to understand it. The more time and effort it takes to understand a piece of code, the poorer the quality is. The less time it takes to understand a piece of code, the better the quality is. And it's really, if you put more effort to write the code, it may become easier for somebody to read it. If you put less effort to write the piece of code, it may take more effort for them to understand it. So there's an inverse law here in terms of quality and effort and time it takes to understand it. So we're going to talk about 12 ways to look at improving the quality of code. So I'll do the count down from 12. And the first one I want to talk about is not even a technical thing, not even a code-related thing to begin with. One of the things I want to emphasize to start with is we should really schedule time to lower the technical debt. Now, we all have heard about technical debt, but I want to say it's not only important to take care of technical debt, but it's important for us to take the time and schedule time to lower the technical debt. Well, so what is technical debt? This gentleman here, Ward Cunningham, coined the term technical debt as he worked on projects in the financial industry, and he realized there is a correlation. In the financial world, we deal with financial debt. Almost everybody, every individual and every organization goes through debt. You may get into a mortgage, you may have other kinds of payments that you have to put together. So debt is not uncommon, but there is a limit to how much debt we can reasonably handle and survive. That becomes very critical. So he coined the term technical debt, just like financial debt, and that is something that we need to be careful about, because if we don't manage the debt properly, we might get into a technical bankruptcy just like financial bankruptcy. In the financial world, if I go ahead and spend a credit card, I realize, oh look, I don't have to pay this credit card bill in full. I can just send a partial amount. Wow, how wonderful that is. I can make a minimum payment and I can have all that other money left for me to spend even more. Well, if this continues, what's going to happen? After a short time, the bank sends me a stern letter. They tell me that I've exceeded my credit limit. But they don't stop with saying that I exceeded my credit limit. You see, the bank doesn't want me to get into trouble. They want me to get into real trouble. So they extend my credit limit. They increase it. Now I have bigger money that I have to spend that I don't own, that doesn't belong to me. If I continue this path, one day I may realize that the amount I owe on the credit card is more than my yearly income. What do I do at that time? Because I can't obviously afford to pay it. The only thing I can think of is to change my name, grow a beard, and move to another state. Just for the sake of record, that's not the reason I left Texas. But the point really is that we cannot sustain that particular model in our lives. That's exactly what happens with code as well. A lot of teams eventually, whether they say it loud or not, may declare technical bankruptcy. You hear people say, oh my gosh, I don't want to work with that module of code. It's something we cannot touch. Nobody understands how this piece of code works. And that becomes incredibly difficult to work with. So we want to really be able to manage this. What are some of the technical debts, for example? Well, here's one sad thing about technical debt. You don't even have to do anything to start incurring technical debt. You have used this particular library or a framework, and you haven't done anything with it. But 6 months goes by, there is 3 new versions of those libraries and framework. And your versions you are using no longer is updated, is current, and you have to update it. And the longer you wait to update it, the worse it becomes to update it. And this is one of the sad things. You will incur technical debt even if you don't do anything. Oh, that schema that we have been using has been evolving and is bent out of shape. We really need to go back and revisit the schema. Oh, but we don't have time for it. That becomes a technical debt as well. So a lot of things, the environment we develop code in, the libraries, the framework we use, our own implementations eventually start accumulating technical debt. Even when we don't put much effort at all, we start incurring it. But it's also important to know what is not a technical debt. Writing intentionally low quality code is not a technical debt. That's a technical sabotage. We cannot really possibly claim that as a technical debt. We have to really work towards minimizing the technical debts that really are debts. But like I mentioned, there are several things that cause technical debt, but it doesn't have to be all or nothing proposition. We cannot say we will never incur debt, so we cannot live in that world. But we have to manage technical debt very, very clearly. So how do we manage this? So one of the things to really consider on projects is to really very explicitly schedule time to start paying technical debt. When we work on projects, we often schedule time for implementing new features. Maybe we also have time scheduled for fixing bugs, but we got to go really beyond that. We have to start scheduling purposefully, intentionally, time for paying technical debts as well. Oh, the first thing I would ask organizations is, what are your technical debt? And when I go to companies, a lot of them will tell you that they have technical debt, but the very first thing I ask them is, can you show me the list of technical debt that you have? So on the wall, in the work area, I want to see a prioritized list of known technical debts. That's the first thing I expect projects to show me. So when I walk in, if they have not written down their technical debt, imagine a relative is in financial crisis, in a lot of financial trouble, and you go to them and say, let me help you, let me put you on a budget, let me help you to get out of the financial debt, And what's the very first question you're going to ask them? What are your bills? And they tell you, I don't even know what I owe to whom. That's even worse. So the very first thing you would ask them is to list down all your debts and the interest rate. Then we'll start attacking from the worst one to the best, easiest one. That's exactly what we want on projects, is a list of all the technical debt, prioritize from the most important to the least impactful. And then we can say, well, here's in front of us, we have a visibility of our technical debt. If this is the amount of technical debt we have with us, it's not going to disappear automatically. So why don't we start scheduling maybe 10% of our time starting to pay these technical debt. So in the next sprint, you are going to spend 10% of your time implementing one particular technical debt, solving one technical debt. You're going to spend 10% of your time. Maybe you will spend 15% of your time, but we'll start scheduling people's time. So when it comes to projects, we often have a lot of time scheduled for development, rightfully so. We also have scheduled time for planning. We also have time for meetings. We often have times on schedule for vacation and sickness. Some companies don't give any time for vacation. Then people take more sick time. That kind of compensates for it. But the point really is we do spend the time scheduling for these things, but among those things, we should also schedule a time for the paying the technical debt as well. But along the way, I want to also talk about one other thing that has been a great learning experience for me. And that is the last one I have on this list, which is the slack time. A lot of times when we work on projects, we are driven so hard to work on the project, it becomes incredibly difficult to improve on what we actually do. And this has been an aha moment for me, listening to this lady here. And Linda Rising once said that a freeway packed with cars is a parking lot. And that resonated, that metaphor resonated so well with me. If you take a freeway and you keep adding cars to it and cars to it and cars to it, at certain point, you have reached so many cars on the freeway literally turns into a parking lot. The cars don't move anymore because there are so many cars on the freeway. So a good freeway, maybe there's a percentage of cars to space that is reasonable for traffic to flow through. Otherwise, it becomes a traffic jam. And exactly the point with our schedule. If you take your schedule and load every minute of the schedule with things you have to do, eventually you have gotten to the point where you as an individual and you as an organization will no longer be able to innovate. And this really struck home to me because I'm a consultant. If I'm not at a client site and if I'm not doing work for a client, I don't get paid, which means I want to squeeze every hour of my day and give it to my clients. And when I heard her say this, I realized I will never be able to improve what I do if I spend all my time on the client projects. And so these days, I very purposefully put time away on my calendar when I do absolutely nothing. And doing absolutely nothing is wonderful because that time gives you an opportunity to go play with things you never had time to play with, to investigate things you want to investigate. I saw a tweet from somebody, I don't know who said this tweet, I don't remember it, but this tweet was phenomenal. The tweet said, "What do you mean we have to fix the fence? We are so busy chasing the cattle." And that's a wonderful metaphor. What do you mean we have to fix the fence? We don't have time to fix the fence. We are so busy chasing the cattle around. Well, of course, if you fix the fence, you don't have to chase the cattle. But sorry, we cannot fix the fence because we are busy chasing the cattle. Automated testing, oh, we can't do it. We're busy fixing the bugs. This happens a lot on our projects. We are never able to improve what we do because we are so tired and taxed to do what we have to do. So by injecting that slack time, we are able to go innovate, figure out better ways to do. So how do we do this? There are different approaches organizations use. I worked with a client a couple of years ago, and different people have different names for this. And they had called it as, Innovation Week. Well, this so happened. It's really hard to convince management a lot of times, but management gets convinced really well when they see results and benefit. So about a few years ago, the company wanted to really have a time for employees to do nothing, so they can do whatever they want to do. And so very reluctantly, the company gave time for a few employees and said, okay, go ahead and spend a week. In that 1 week, the team went on to implement a mobile solution they always talked about but never ever had the time or the courage to go try. And the minute they implemented a prototype of this, seeing it in action was like a light bulb going in their head, and immediately they turned it into a product, and the company started making a profit on that product that didn't even exist only a few months earlier. Now the company organizes Innovation Week. The employees don't ask for it anymore because they have seen the benefit of it. And every year they have 1 week every 6 months where employees come to work and they can do anything they want to do except work on their own real project. And at the end of the week, they talk about what they did. I'm working with another client where what they do is something a little different. Their employees every year write a proposal, and once the proposal is approved, they are given a few weeks to a few months where they don't have to show up to work, but they get paid. And they can work on this other project they got permission to work on. And organizations are figuring out a lot of different ways to make this kind of innovation happen. And the reason really is we can never improve on what we do in the middle of just doing what we already are doing. So that kind of slack time is extremely important. This resonated really well when I read this really good book, The Guns, Germs, and Steel by Jared Diamond. And Jared makes a really interesting point in this book. He talks about a time when most of the humans were savages. Today, the good news is only a few of us are savages. The rest of us are more civilized. But it was a time when humans were savages. And they had to go out and hunt. If you wake up in the morning and you don't go to hunt, that's a day of starving for you and your family. So you have to go out and hunt every single day. And when people were hunting predominantly, they were pretty much, savages. Well, eventually humans figured out, and he really draws a really nice timeline. Eventually humans figured out they could do agriculture and farming. And you could grow grains. And you could domesticate and grow a lamb or a goat. I mean, can you imagine the discovery when you could have a lamb next to you, you can play with it all day, and when you're hungry, you can just eat it. This is amazing, isn't it? So then they realized, I don't have to go to hunting because I got a little goat with me today. And I can, okay, what are you going to do with your free time? Gosh, I don't have to go hunting. Maybe I will start singing. Maybe I will start painting. And he shows how the time when agriculture was started is the time when civilization was starting also. And all the culture and everything started when we no longer had to go run for food. And this again really resonates well with this idea that we should really have slack time for things, because if we don't have to hunt for our work every single day to get the work done, we begin to really get better at what we do. And so that slack time is extremely important. So that's why it's a very non-technical thing, but a lot of times the non-technical things really make a very high impact on our ability to make better what we do. And so scheduling time to pay technical debt and also having a slack time becomes extremely important for us to be able to do better. The next thing I want to talk about here is to favor high cohesion. Best time to ask questions or make comments is when you have it. So please don't hesitate or wait until the end. Any time is a great time. So the next thing I want to talk about here is favoring high cohesion. Some of the most important principles keep coming back almost every single line of code we write. It doesn't matter. I think some of these principles are pretty timeless. And one of them is high cohesion. So what is cohesion? Cohesion is where a piece of code is narrow, focused, and does one thing and one thing really, really well. And a cohesive code is a better maintainable code. So why is cohesion so important? Well, it's very narrow, focused, and does one thing well. And because it's narrow, So imagine a piece of code that does several things. Well, if a piece of code does several things, it has several reasons to change. If a piece of code is doing one thing, it predominantly has one reason to change. So it really comes down to the frequency of change. So a more cohesive a piece of code is, the less frequently it actually changes. Well, a software system has to change over time, but you don't want to change a lot of the software every time the entire software has to change. So you want to compartmentalize it, modularize it, and minimize the change that happens to different modules over time. That becomes very important. High cohesion code also results in low cyclomatic complexity. Cyclomatic complexity is the number of edges and branches that your code is taking. The more decision points a code takes, the more complex a piece of code is. It reminds me of an experience. I was with a client when one of the developers, when I was talking about quality of software, he said, I want to show you something, come to my desk. So I go to his desk, and they've been writing software for a good 30 years. And they have all this code in the version control. So he grabs this little handle, drags the timeline to 30 years ago, or about 25 years ago, and puts the cursor on it. And I can see this function. That day is when this function was born. It's so beautiful, little, you can see its little fingers and little parameters, its cute little function. And you could see that's the day proudly it was born. And then he points to me on the monitor and he says, look over here, that's a cyclomatic complexity of this code. And the cyclomatic complexity of that little code was 5. And then he drags the timeline through that 25 years. As he's dragging the timeline, you can see this file, this function turn into a monster in front of you. And then on this day, it's sitting in front of you. The name of the function is still the same. And that's the only thing that's still similar. It's completely changed and evolved. And it's big and monstrous. And then he says, look over here. And the cyclomatic complexity of that very function now was 864. He said, that's what we do to code in this company, right? I mean, that's scary, where this little cute function turns into a monster, and then he says, now nobody wants to work on this function, right? No, everybody, the day it was born, everybody wanted to come and, fondle it, right? Oh, this is so cute, so cute. Now everybody's like, no, I don't want to come. This is kind of like humans, right? Everybody wants to come see the baby. They want to play with it. When you get older, everybody kind of stays away from you, right? It's kind of like that. It feels that way. And then that becomes really a monstrous, complex code. Nobody wants near it. And then that happens as time goes on. It becomes really, really hard to work with. Well, the next thing to think about is coupling. Coupling really makes it hard to maintain code. So a good software should have high cohesion and of course, low coupling. Well, people always will tell us to reduce coupling to favor loose coupling. Well, sure, I agree with it, but I want to go a step forward from that as well. What about eliminating coupling rather than just reducing it? Well, is it even possible? Well, first of all, tight coupling makes it really hard to extend code. It becomes really hard to test the code as well. But we can lower coupling. And in general, we want to favor loose coupling instead of tight coupling. But I would rather eliminate coupling as much as possible, where possible, than even making it a loose coupling. Well, in general, we can argue in the languages that support interfaces, depending on an interface is loose coupling, depending on a class is tight coupling. So we definitely want to favor interfaces where it makes sense, of course. But what about removing coupling? And I think we're not paying enough attention to remove coupling after all. Reminds me of an experience. I was in a conference called Software Design and Testing Conference. This is a kind of a little bit of a different conference where people don't listen to talks, but instead they have open space where people come up with a topic and they discuss about it. One of the topics that particular day was, we love automated testing, but mock objects make it really brittle and hard to test. This was a topic very interesting for me, so I kind of walked in. I was by the door and listening to about 30 different developers in the room saying how they all are bought into TDD. They do automated testing, but mock objects make it really, really hard for them to work with these tests in the long run. After listening for a few minutes, I blurted out saying, hey folks, I've got a question for you. Have you considered maybe your test is really hard because your design sucks? And by saying it, I made everyone in the room angry. And they all looked at me and said, who are you? Why would you come and tell us our design sucks? What do you know about design? I said, look, I design software and it sucks. I thought you guys are like me. Well, then we said, why is it so hard to write tests? And they said, let's take an example. That's great. So we put an example on the board and we talked about how we would design this. And then when we went about talking about it, is when I suggested maybe this is a coupling you have in front of you, and because you have this coupling, you obviously want to mark it away. But have we considered the fact that maybe this coupling shouldn't really exist? Maybe this coupling doesn't belong here. Maybe it should be removed or at least be moved elsewhere. The next morning I wrote a blog entry, and my blog was called Knock Out Before You Mark Out. And the point is, I don't want to mark out my dependencies. I want to knock out my dependencies as much as I can. And only when I cannot knock it out do I want to consider using a test double, marking our stubs. So here's a little example of this. Notice that the code on the left side, the gray code, is depending on the blue code right in the middle, and this blue code is depending on the red code in the right side. Well, I want to write automated test on the middle code, the blue code. Well, that's really hard because the middle code has a dependency on its right side. Almost every single test I'm going to write on the middle code now is going to require really, that was not a button to press, I guess. Okay, so everything on the middle code is going to have to require a mark object for the code on the right side. Not much fun at all. That's not going to go work really well. So here's an idea. Why not maybe reconsider this for a second? Ask the question, why does this code depend on this code? Well, the answer is actually pretty easy when we ask the question that way. The reason this code depends on this code is, in the middle of its operation, it wants to go run out and get some data. Well, wait a minute, why don't we tell this code, no, you're not going to go run out and get the data. I'm going to give you the data that you want rather than you having to go get it. It's kind of like, you know, I'm here, and right in the middle I can say, oh, pardon me, I'm going to go get a cup of water. I could run to get a cup of water, or I could be here and a cup of water could be given to me. I don't have to run for it. Well, there's quite a bit of difference here. If I'm given a cup of water, it serves my need. All I want is water, but I don't have to care about where I get the water from. On the other hand, if I have to go get a cup of water, I got to figure out where the water is that I can go get it. Exactly the point in this case. Why don't we move this a little bit? So we move the dependency out of this code in the middle. So now we are going to give the pieces of data that it wants. Well, clearly this code requires no such marking anymore. We don't have to worry about it. Well, this code became a little bit more burdensome. But in all honesty, it was not too different from what it had to deal with already. So the testing of this is not going to be even more complex than it was, but the testing of this code become a lot simpler than it was before. So one of the things I tend to do quite often is ask the question, can I remove dependency, or at least move the dependency if I cannot remove it? And that seems to eliminate certain burden quite a bit. So we want to favor high cohesion, and we want to favor low coupling, or eliminate coupling where possible. But the next thing I want to say is we want to program with intention. How many times do we write code which is pretty accidental? You are looking at a piece of code, it doesn't work. And somebody is next to you helping you figure out why this code doesn't work. And then they have a great suggestion for you. Try putting +1 and see if it works. We all have seen this, right? And you put a +1 and sometimes it works. Now you have another problem. It works, but you don't know why it works. And this becomes really hard to work with. These are accidental programming. We are desperate to make the code work, but we have to program with intention. I want to be able to drive this code and say what causes this code to work. I'm sure we all have come across this particular case that I saw on the internet. We can definitely sympathize with this developer because the comment clearly says the situation. It says, when I wrote this code, only God and I understood what I was doing. Now God only knows. And this happens a lot with code we write, because you look at this code and you know you wrote it, but you have no recollection as to why you ever did this. It becomes really hard at this point to program with the code, and it's very, very frustrating when you run into code like this. So I like to use Ken Beck's rule of simple design quite a bit. He outlines 4 rules for simple design. Martin Fowler talks about this in his blog, and the first rule he says is, the code passes all the tests. There is an implicit assumption there. There are tests actually. But the code passes all the tests. The second rule he says is reveals intention. The third is there are no duplications. And finally, fewest elements. He says that these are in the order of high priority to low priority. I generally like the last one really a lot. In fact, people often complain about my overindulgence on the fewest elements. I'm one of those guys, the annoying person on the team, asking the question, oh, why do you need this? Why do you need this? And I want to minimize, 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 and that's called parsimony or minimalistic design. And I really like that a lot, to be very minimalistic, having fewest elements. Avoiding duplication of code and configuration and intent and effort. And finally, of course, reveals intention, where the code clearly conveys its purpose and it's very intuitive to use. And of course, it has to pass all the design as well, all the tests as well. But one of the ways that we can actually achieve this is by writing tests as we write the code. Because when we write the test, we are being very purposeful. We are being very deliberate when we are writing the test. We're not throwing the code together out of whim or frustration or desire to get something working, but instead we are asking the question, what do I want the code to do? And we write assertions for it, and then we come back and write the code for it. That's a really good way to write that as well. The next principle here is avoid primitive obsession. We have this tendency to write code at the lowest level of abstraction. And this is one of the things that I would say probably has gone bad over the past about maybe 20 years. 20, 30 years ago, a lot of people coming into programming substantially spent their time in school learning functional style of programming, and then, of course, other styles of programming also. Fundamentally, universities unfortunately shifted in the late 80s to early 90s. They abandoned functional programming. Not all of them did, but majority of them did. They abandoned functional programming, and they started teaching object-oriented programming. They started using C++ as the predominant language. They started using Java as a predominant language afterwards. And eventually, there is a generation of programmers who grew up without getting a taste of different programming styles. And now, a lot of universities are shifting back. Not all of them yet, but some of them are beginning to do that. One of the things that I've had, I would say luxury, if you will, is I teach at the University of Houston, but I don't live in Houston. I live in Colorado. I teach remotely. And the university said, we don't care where you are, as long as you teach and as long as the students are happy with what you teach, we are fine with you. So I went back to them and said, hey, I really want to teach a course on programming languages. And they said, we don't care, teach whatever you want to teach. This was a luxury because I could do whatever I want to do in this course. So what I did was I introduced the course where I actually teach 8 languages in the course. But the students can use any language they want. They don't have to use the languages I use. So it ends up that the students collectively begin to use about 20 different languages in the course. And we get a really good taste of structured programming, object-oriented programming, functional programming, languages that are purely functional, and so on and so forth. And my goal is to really come to the point where we realize there is no one way to solve the problem. These are tools, and we have to really figure out which tool makes more sense on a given day for a given set of problems we are dealing with. And one of the things out of that also is we should really learn to raise our level of abstraction and use functions and libraries and tools given to us rather than having to create the whole thing over and over. So I'm going to say imperative code is packed with accidental complexity. This is one of the sad things is most of us have been programming in imperative style for a good 20 plus year, which means we've been programming with not a very sharp tool over these years. This is like giving you a blunt tool when a sharp tool is needed, and we've been trying to get the work done. I spent most of my career programming in imperative style. And I'm a late bloomer. I eventually figured out functional programming, even though it's been around for a long time. And I'm beginning to really understand why that is a lot more powerful than what we have had in our hands. Let's look at an example of this real quick to just get a feel for it. So what I have here in front of me is a function called is prime, and all that it's doing is it's returning to us whether a given number is prime or not. Let's not worry too much about this. There could be many, many ways to improve this, but that's not my focus. My focus is right here. I've got an n which is 101 and k which is 51, and I got a function called compute, but what is this function compute supposed to do? Find the total of square root of k prime numbers starting with n. So I want to find the total of the square root of the k prime numbers, but they should start with n. So how do I solve this particular code? Well, what we would do in the imperative style is you would say index equals n. That seems like a good starting point. You want to start with n, so it's an index. And then what do? Count is equal to 0 because you want to do k number of values. Oh, you need the result, of course. Result is equal to 0. So what did we just do? We wrote a lot of code and did absolutely nothing. And that is one thing. We could say, gosh, that was a lot of work. I need a cup of coffee now, right? That's a lot of work. And we did really nothing at all, but spent all this time initializing variables. These variables have really good name. These variables are called garbage variables. And in fact, there's one evidence why these are called garbage variables. I'll tell you why. Because you would very rarely see people write int index, int count. They normally say int I, int C, int R, or T. Because we tell these variables, you don't deserve to live. Right? Absolute disrespect to these variables. You don't deserve to live. I'm going to give you random variables because I don't care about you, right? That's why we're conveying an intention right there, and the intention is I don't care. So we have to be better than that. Then what do? Well, eventually, of course, you want to return the result that you have with you. That's what you want to do. But then let's do the work. What do? While, and I'm going to say count is less than k. Stop right there. Is it less than k or less than or equal to k? How many times do you ask that question? Every single time. And how many times are you sure? Never. Because you type that and then you think about it and say, is it less than or equal to? And then you look away, you look outside. You're trying to really understand this. You are going to the bathroom, you stop on the way. Is it less than or equal to? Because you're never sure about it, right? And it's frustrating. What is that? That is accidental complexity. And then what do? Then you say, all right, I'm going to loop through. If index is prime of index, great. The index is a prime number. Result is plus equal to math.square root of index. And then, of course, I'm going to return the result. Is the code correct? I heard no. Somebody murmur over there. No, it's not correct. What did I forget? Increment what? Index. I have to increment the index. Let's increment the index. Index plus plus. What else do I need to do? Increment the count. Count plus plus. Is it correct now? What's wrong? It should be outside. Okay. Is it correct now? No. Index should be, count should be, how rude. One should be inside, one should be outside. What do now? Stare at it. Is it correct now? Did you just notice the entire room went from no a few minutes ago to wondering? In fact, I'll tell you, programmers are the smartest people on planet Earth. Because when you show a piece of code and ask the programmer, is it correct? What do they tell you? They never tell you it's correct. They say it looks good. Because they know very soon it won't be correct. So you never say it is correct. It looks good. Because when they find fault at it, you say, it only looked good. So what do you think of this code? It looks good. And what did it do? It increments the count, and it increments the index. I can take the good faith and run it and see if it gives us some result. It gave us some result. We'll be in good faith. Okay, it works. But that's a lot of work. When you write code like this, how do you feel? This problem is not a complex problem at all. I would argue the problem is simple. The solution is complex. I have a little, opinion about this. And that is, it is code like this that prematurely makes programmers into managers. Because they say, I am done. Let you clowns deal with this. I'm going to go spend my time elsewhere. And this is when they're like, this is not for me, right? This is the quickest path of exit. I mean, you are the survivors because you're like, I can handle it. But others have exited a long time ago, right? They're like, no, not for me. I'm going to be a manager of software development, not developing software. That's what happens because that's way too complex. This is really hard. And imagine doing this in every turn, every code we deal with. It becomes very, very complex over time. But thankfully, we don't have to work that hard. It is unfamiliar to us, but we can figure out better ways to do it. So let's try this again. Let's take this exact code for a second, but let's do this one more time. This time we're going to say over here, let's bring in a stream. So stream.iterate. We start with n, and then we say given an element, element plus 1. That becomes what is called an infinite stream. So the infinite stream says, I will start with n, and I will keep giving you one value at a time as long as you ask me for another value. So it's kind of like on demand, like a pay-per-view. So you keep asking, you give me more, and it gives you more, but not otherwise. So then we can say return, and we can start with that. Then I say filter. Given a value, tell me if it is prime. Then I perform a map operation, math square root, and then of course I'm going to perform a sum operation on it. So this is going to be mapped to double, but I don't want to be working on all the values, but limit k. Wait, is it less than k? Is it less than or equal to k? It's k, damn it, keep moving. So we don't have to be spending our time on these questions. So you're saying, given all these numbers starting with n, give me only prime numbers starting with n, but give me the square root of the prime numbers starting with n, but give me only k of them, and then total them up and give me the result of it. I don't want to do any more work. So you can see how that code we saw, which is enormously complex, becomes a lot simpler. But of course, we had to know how to write this code. There's a learning curve here. But once we get past the learning curve, it becomes a lot more easier to work with this because the code flows naturally here. You start at the top and say, given all the numbers, get me only the prime numbers, but get me the square root of them, and then only get me that many, and then perform the total. That becomes a lot easier to express it, and that is inherently simpler compared to the code we saw just a minute ago. So functional style code is declarative in nature. Declarative code has less complexity compared to the other one. A good code should read like a story, not like a puzzle. The code in the top was a puzzle. You invite team members to decipher it. And you say, what does this do? And we are trying to dance around. Did you increment here? Did you increment there? It's a puzzle we are trying to solve. But what happens if you create puzzles at work? When you create a puzzle, your colleagues come to work and say, I don't understand this code. And then they sit there for hours, sometimes days. And eventually you hear a scream in the next room. That's when they figured out what your code is doing. And they're like, I got it finally. But keep in mind, if you give a puzzle for them to solve, and when they eventually solve it, you think they're going to be quiet? They're going to be writing the next puzzle for you. In the meantime, you got a production software to release. That's not going to be fun at all. So I want the code to read like a story, not like a puzzle. The code in the bottom is like a story. You just come and read through it and you get it. Well, the beauty of this is, the code on the top was the imperative style code. Imperative style code is where you tell what to do, but you also have to tell how to do it. The code in the bottom that we saw is a functional style code, but functional style code is declarative in nature. So a declarative code is where you tell what to do and you let the underlying libraries figure out how to do it. So in this case, one of the reasons why we are finding it easier to understand the code in the bottom is because it's declarative. You focus on what and not on how. So we need to really avoid this primitive obsession. Primitive obsession is where we try to write the code at the lowest level possible. This reminds me of an experience. I do quite a bit of code reviews, and I saw a piece of code by a developer, and fortunately we had a lot of automated tests. And I looked at this code. It was about 30 lines of code, and I'm looking at it, I'm getting a sense, I know what this is doing and I've seen it somewhere. And I go through it a few times. Once I realize what it is doing, all that I did was I quietly commented out the 30 lines and wrote one line from the JDK, because the JDK already has a function to do it. I just wrote that one line, made sure all the tests are passing, and I quietly checked in the code, didn't say a word. About an hour went by. I saw the file again change in the version control. So I was curious. I looked at the file now, and the developer who wrote it saw the file has been modified, looks at it, and quietly removes the code that was commented out and checks it in. Well, that's one of the ways to realize we don't have to be writing all this code. There could be other methods already available. We shouldn't be the first person to be writing this. We can reuse quite a bit of that code. The next thing I want to talk about here is to prefer clear code compared to clever code. Now, we all try to write clever code from time to time. One of the reasons we like to write clever code is, in all honesty, it feels good to write clever code. You take a pride and you say, I know this was a simple problem, but I feel good that I wrote it this way. When you write a clever code, the proverbial hand comes and pats you in the back. It's so soothing. It's like, wow, that was so awesome. I had one such experience, actually, which was even worse. I was given a problem by a client, and they said, we need to fix this. I looked at the problem. It would have taken me 10 minutes to fix it. Oh, no. How could I solve a problem in 10 minutes? I don't want to solve this problem. I want to solve the mother of all problems. So I spent an hour solving not just the problem, but a meta problem. And when I solved it, I had an out-of-body experience. Literally, I was sitting and working, and I can see Venkat get up, walk around, and come and hug me and say, you are awesome. It felt that good. And I checked in the code, and I felt so proud because they gave me a problem, but I solved the mother of all problems. A couple of weeks went by, and I got an email saying something absolutely catastrophic has happened in production. And I looked at it, and I immediately responded saying, got it, I'm going to fix it, I'm working on it. And they replied back saying, oh, we know you will fix it because you're that smart. I replied back saying, no, I will fix it not because I'm smart, I will fix it because I caused it. Because that little solution I had put in place failed in ways I never ever imagined. So what did I do? I rolled back my code and put the 10-minute change that I could have put in the first place. It's been about 7 years now, no problem at all in production, no worries. So I've learned my lesson. These days when I write code, I finish a piece of code, and my little mind tells me, oh, that's clever. I delete it immediately, and I start over. I don't want to write clever code, I want to write clear code. And this haunts me quite often. Well, here's a really good quote. Ableton and Sussman say, programs must be written for people to read and only incidentally for machines to execute. What a wonderful way of thinking. This is a way to say, don't work too hard on making it better to write it. Focus instead your efforts on reading the code. That becomes extremely important. I'm going to say 10% of the time we write ugly code for performance reason. The other 90% we do so just to stay consistent. And that is something we all do. I was at work a couple of weeks ago. A developer came to me. He sits down in his chair. He puffs a little bit and he says, Venkat, I have a question for you. I said, what is it? Well, I got this developer over there in this corner of the building, and he has written some really ugly code. And he tells me it's got to be that ugly for performance reasons. I just wanted to ask you for your comment. I said, I do have a question for you. Is the performance good? He said, no. I said, so what do you do now? He's like, thanks for the answer. Well, that's the whole point, right? So now you're stuck with a code that doesn't perform and you can't maintain. And how do you really improve this? So those who sacrifice quality to get better performance may actually end up with neither of them. And this happens a lot. And this has been my experience. And it's not easy. I remember very clearly working on a project where, like every developer, I want to optimize and make every line of code faster and faster and faster. So I told myself, I'm going to ignore all those things. I'm going to focus on beautiful, maintainable code. And I did. And I wrote it. And when I finished it, the code, how did it perform? It performed beautifully well. Why? Because there were no users. And so I put it in production. It worked really well for about 2 years. After 2 years, we had enough data collected. I got an email from a user one morning saying, do you realize every click on this page now takes 15 seconds? I said, yep, I'm going to work on it. So I wake up really early one morning, and what did I do? I went through the code, and I made every line of code ugly, because that will give me performance, isn't it? And whatever we would think about when we're writing code, oh, this loop should be really the other way, change it. And I made every optimization possible in the code, and I finished it. After 2 hours of changing all the code, I ran it, and I looked at the performance, and now it took 15 seconds. And I was like heartbroken. I'm like, gosh, I wasted 2 hours. So it doesn't matter. Any of this doesn't matter. What did I do? I just rolled back the code. I put it back to what it was before. Why bother changing all the code when it doesn't give you the results? Then I started bringing in more profilers and starting running on the profilers. And then I discovered, out of the 15 seconds, most of the time was spent on one function call. And that was not even the function I wrote. It was a function in the level below. And the minute I saw what that function was, I started reading into it. 5 minutes later, I made exactly one change to the piece of code. And after that one change, the performance was 33 milliseconds. And that was a learning experience for me, because I was struggling here with the code when all that struggle resulted in absolutely no benefit. Not knowing where the problem is. How could we possibly know where the real problem is when we are writing that code? If you write the code in a way it's elegant and maintainable, you can go fix the part that needs to be fixing. If instead we convolute every piece of code everywhere, how do we then come back to improve the performance? So I feel that any performance talk has to really have the context. Is the performance really critical here? One of the things I often tell people is never look at raw performance. Raw performance is the most stupid thing ever to do. Just to look at 2 pieces of code and say, that works faster than this. I don't care that it does. Because in my context, that code that you say is going to be fastest is called very rarely. So why bother optimizing that piece of code to that degree of performance when it's very rarely called? So where is the code that's being called millions of times? Look at that code, measure that code's performance, and see if it's adequate. If it's adequate, don't bother fixing it any better. If it's not adequate, then put the effort to improve to get the result you want, not otherwise. Tony Hoare said this really well. He said there are 2 ways of constructing a software design. One way is to make it so simple that there are obviously no deficiencies, and the other way is to make it so complicated there are no obvious deficiencies. So the point really is, when the code becomes so convoluted, we don't even know what's broken in the code, and that becomes really hard. The next thing I want to talk about is somewhat non-technical, but a lesson I've learned really well. I call this applying the Zinsser's principle on writing. This came to me from a totally non-technical book. I was given a copy of this phenomenal book, a very old book. This book was written a good 30 years ago, called On Writing Well. And this book talks about writing good English. This book talks about how to really write non-fiction. And when I started reading this book, several light bulbs went in my mind. I was like, wow, there's a better way to really write these things. He's got really, really good advice in it. Since the time I've really benefited from this book, I bought this book for my son who was 10 years old at the time, and he read this every summer. So this was his reading thing for every summer. So he would read this every summer, and the way I know that he read this is, we would be reading something, and he would suddenly quote from this book, and he would say, oh, Zinzer says this, and I think this particular sentence here is really poorly written, or Zinzer says this, and I think this sentence is really written well. He would critique things based on what he has learned from this book. Since that time, I realized if a 10-year-old can benefit so much from that book in improving his writing, and his writing is really good thanks to many reasons, including this, I started buying this as a gift to almost every kid I meet ever since. I'd be in a random city, and some friend would invite me and say, come have dinner, and I would know that they have a child, and I would, on the way, go buy this book and go to their place. And when I go there, I would say, here is a book, I really like it. Next time Uncle Venkat comes back to your house, I will ask questions from this. The kids really get scared, and they never call me back after that. But the point, though, really is, I think there really is a very important things to learn from this. Well, he talks about 4 principles for writing good English. As I was reading through this, I realized these 4 principles for writing English is not just for English, it is for writing code as well. Because what we do when writing code is what we do when we write English, we communicate. The very first principle is something we all have seen several times. The first principle he talks about is simplicity. He says when you're writing, keep your writing very simple, don't make it very complex. That's exactly what we say when we write code as well. His recommendation for English is not so far away from a recommendation for writing good code in that sense. Where does complexity come from? Complexity comes from lack of cohesion. When a piece of code does several things, it becomes overly complex for us to understand. So we can keep code simple by making it more cohesive. And we can also make the code easier to understand by removing coupling as much as we can. The next principle he talks about is clarity. He says when you're writing something, make it very clear for the reader. Now, I've written quite a few things. I've read a few pieces of work by other people also. And I've noticed a common mistake other people make and a mistake that I also make. And that is when you are writing, you know all this idea in your mind. It's very clear in your mind. And you dump it on a piece of paper. And somebody reading it gets very, very frustrated. And then why? Because you have not taken them through a logical flow of thoughts. Instead, you have poured these ideas in your mind, and they may not really walk them through from the unknowns to the knowns really well. This is exactly what happens in code. You see this developer changing this variable here, and suddenly changing that variable, and calling a random function, and then changing more variables, and you're sitting there and trying to figure out what's happening here. And clarity is gone. The code works, but you don't understand the flow of logic, because the developer knew what the developer was doing in their mind, but they didn't translate that to a clear sequence of transition in the code. So mutability makes the code less clear as well. We can eliminate the problems with clarity by removing mutability quite a bit also. Then comes along brevity. Brevity, he says, avoid using long sentences, avoiding using long words, avoid using long paragraphs and long chapters. You probably remember back in the 20 years ago, books really were that big. Books served 2 purposes. Occasionally you could read through them, but otherwise you could use them to improve your biceps. And these were like monstrous books people wrote. We don't see them anymore. Books are much shorter. Part of the reason is we got a lot of references on the web. But another important reason is we figured out nobody reads these books if we write long books. We don't have patience for it. So brevity is very important. And in terms of brevity, you really want to, in the code level, you want to keep functions short. You want to be able to keep classes as small as possible. Long functions make it really hard to understand, so you want to have brevity. And tying these 3 together, you also want to make sure the code is very easy for somebody to understand. Choosing good variable names can help understand that also. Let's not mistake what brevity means. Brevity doesn't mean we use single letter variables. That's cryptic, not brevity. That has to be easy to understand. That's very important too. And another thing to consider is to consider the reader when you're reading it. I fondly remember one experience. A good 30 years ago, I wanted to go to the United States and get a degree, which means you have to take the GRE exam and various other exams. And when I was preparing for it, I realized something. I can do math really well. I can do analytical things really well. But English is something I cannot do. I did not know how to speak English until I was 17 years old. So I had been speaking English for a good year by the time I had to prepare for GRE. And I looked at the GRE English material and I was scared because the words were out of this world. They were from hell. And you look at these words, I could not get past the first page with A words. Forget about going to B words and C letters and so on. And I was struggling with this, and I did a very smart decision. I told myself, I will max out math and analytical, and I will fail English. And I did. And I literally failed English, and I aced out math and analytical. The university looked at my score and said, this guy can't speak, can't read, but he does math really well. Yeah, let's take a chance. I'm so glad they did. And then I went to the US, I found something absolutely phenomenal. In the 30 years, no one ever came to me and used a word from the damn GRE book. Every word people speak, I understand. I never had to say, could you hold that thought? I want to look in the dictionary for that word you just said. People speak in a way you can actually understand it. And then I realized, forget about building the wall. The GRE book is already good enough to keeping people like me away. So the point really is, it's incredibly complex. And then you ask the question, what is the purpose of that? The purpose of that is to pass an exam which has no benefit other than passing the exam. And I have absolutely not used anything from it. And we write things. This is what we do in our programming world. We say avoid jargons. Avoid using words that make no sense to anybody. Make it easy to understand, make it easy to communicate. That becomes important. The last piece of advice he gives to write better English, he talks about humanity. And I struggled with that a little bit. I said to myself, oh, humanity, we don't have to worry about that. We write code for lifeless machines to run. Why should we care about humanity? And I realized that is probably one of the most important principles, actually. Because humanity, we cannot forget it. When we write code for a lifeless machine to run, our design suffers. When we are humane about not only who is running the code, but who is using the code, who's reading the code, and who is going to come back and maintain it, our design becomes a lot more humane in terms of its efforts. So humanity is something we should really care about. But programmers have this tendency to promote this inhumane kind of attitude. The other day I had an optometrist looking at my eyes, and while she was looking at my eyes, she asked the question, what do you do for a living? I said, I'm a programmer. And then she went on to talk a little bit about my eyes, and then a few minutes later she said, what do you do for a living? I said, well, I told you I'm a programmer. And she said, yes, I heard you the first time, but I just wanted to confirm because you look almost normal. And that is something that people think, right? So somehow, maybe if we're programmers, we should really be antisocial and like that. But I have this theory. Programmers are not antisocial. We're just social among the right set of people, that's all. So, I could be in an airplane for, 12 hours. And I would be sitting next to some person. I don't want to be bothered. Don't talk to me. Don't ask me questions. I got better things to do, like coding. I'll be just coding for the 12 hours. But the minute I realize the dude next to me is a programmer, it's a riot after that. Because I got so many things I want to chat about. And I mean, how could a flight not be fun when you can argue about checked versus unchecked exceptions, right? So there's so many important things to talk about in life when you have a programmer next to you. And that's exactly the point, that it becomes really humane. And that is something to consider. These principles that he talks about for writing good English really translate to writing good code as well. Oh, talking about comments. This is one of my pet peeves. I really hate comments that tell me what the code is doing. I don't want to comment what, I want to comment why. And that's something important to keep in mind. When we write comments, we should really think about what we are trying to convey. I'm sure you have seen your share of code like this. The other day I came across a piece of code that said I++ and with the most useful increment after that. I was so thankful. As I'm getting older, I'm no longer sure if it's a plus or something else, and I'm trying to zoom in. That increment was so helpful. Or the other day I saw another piece of code, class something, and then it said implements, and then it's implements comparator X with a comment implementing comparator, or something to that extent. And it is just repeating what the code is doing. Part of the reason I think this has gone so bad is people who teach courses. And I can blame them because I'm one of them, right? And they insist, you will write comment for every single line of code. Students come to my class and they are so angry. Every professor before you told me write comment. Now you're telling me remove it, unfair, right? And I'm like, no comments, no comments. And they're getting very angry. I've been writing comments all my life now because they told me I'll fail if I don't write comments. You tell me I'll fail if I write. What gives? And the point is, we should comment why the code exists, not comment what the code is doing. I'm going to say most of the comments are written to cover up bad code. And if somebody writes a piece of code I cannot understand, and they tell me, I don't understand this code, write a comment like, no, I don't understand this code, refactor. And that becomes very, very critical. I want the code to become self-documenting and expressive. I'm not saying don't write comment at all. Write a comment to tell me why the code exists, not what the code is doing. If there is something very, very, very special that is a decision that you went through and you want to explain the reasoning for that, write a little comment for it. That's great. But not just explaining every step what the code is doing, because the code should become really self-expressive. A good code is like a joke. When was the last time you told a joke and everybody in the room kind of stared at you? The worst thing you ever do when you tell a bad joke is explaining it. So if you ever tell a bad joke, the right response after that is this word called never mind. Never mind. What was it? Never mind. Forget the joke. But the worst thing you ever do is you tell a joke and nobody gets it. They stare at you and you say, no, let me explain it. And then you explain it, and when you finish it, people stare at you and say, yeah? So what's funny about that? Let me no, please. This is a very long evening the minute we go into re-explaining. So what do you do when you tell a really bad joke? So here's my rule. You tell a bad joke, you say never mind. Then you go home and you quietly sit down and you refactor that joke. And then you try it with a new group of people. So a good code is like a good joke. Trying to comment the code to tell what it's doing is like explaining a joke. And we never want to be able to do it. So as a result, and the code should be extremely clear. And if it is not, we should refactor it to make the detail clear rather than having to explain it using comments. The other problem really is when you write comments, how many times have you seen this? The comment tells you one thing and the code does something completely different. And now you're like, which one is true? Is the code correct or the comment correct, right? And also I've seen comments where there is comments that just pour out emotions. And you almost want a napkin when you're reading this comment. You feel like weeping, right? Because this person has poured his heart into it. I remember working in a company where all the people who wrote the code had gone away. So this was a new set of people maintaining this code. And there was a lot of comments, And a couple of years later, the company decided to organize a day when they invited all the people that used to work with. And I walked into the room and I saw all these people chatting. I went to this one guy and said, hey, are you LK? He was very happy. He said, I am LK. Have we met before? I said, no, but I've read all your comments. because I could hear his voice and know who it is from the comment. I mean, I've been in the comment all these years, right? So you know from the words they speak, I know who you are. And that's when you know you've gone overboard with it. So I complain a lot about programming. I think a lot about programming. And this was very frustrating for me. I was in Washington, D.C. to speak in a conference, and I had to take a shower, which is a good thing. So I got into the bathtub to take the shower. As soon as I got in, I wanted to use the shower, and I saw this and I was so angry. Now we live in a world when you're angry, it doesn't matter what you're there for. You should immediately tweet about it. So I forgot about showering now, and I grabbed my phone, took a photo, and I had to tweet it. And the reason I got so angry is, this is just a way to use the shower. But when you come to use the shower, it says, pull to turn on. And I got so insulted because immediately I tweeted, and my tweet said, those who cannot design are condemned to document. And this is so true in most of the things you see today. And I get really angry when I see this. Why can't you make things intuitive rather than documenting it? You see this method, int p1, comma, int p2, comma, int p3. Why me? What does this 3 int mean? There's a documentation that explains. P1 stands for, like, why don't you just call it that, right? That becomes really hard. And there is no limit to this. The other day, I wanted to take a medicine for cold. I took the medicine, and I turned it around, and on that label it said, please take 2 tablets by mouth. I'm like, what are you suggesting? I don't know. And I feel really ridiculous reading these things. Do you have to really tell me every single thing? And now I'm like, what are the other options? I'm really tempted. This is a cold medicine, for crying out loud. What else do you expect me to do? And that is the world we live in. We got to document the hell out of everything we do. So comment why and not what. So order 3. Oh, what in the world is 3? How about large cup of coffee? Maybe 3 was something else. Why not use an enum maybe to tell what that value is so we don't have to write a comment for it? So document code using well-chosen meaningful names. Use comments to describe its purpose and constraints. Don't use comments as a substitute for good code. So tell me the reason for its existence. Tell me any constraints I have to be worried about. And not going through and telling me what every line by line, intra-method comments that tell me every line of code, what it does is not helpful. We need to really avoid long methods. We can talk a lot about why we should not do long methods, but in a sense, we talk about methods that are way too long. But what are some of the reasons why long methods are a bad idea? We could say long methods are a bad idea because it's hard to test, hard to maintain, hard to understand, hard to debug. They lead to duplication. They are, long methods become longer as time goes on. We could keep listing these reasons for it. And we all suffer through long methods a lot. One favorite memory comes back. I was speaking in Devox, Belgium back in November 2015. And Devox, Belgium is where you're in an IMAX theater. As a speaker, you're this big in this room. And there's a dark room in front of you. You cannot see who's in front of you. And I'm standing there and asking the question. And I asked the question, what's the longest method you have seen? There are like 800 people in the room. And right from the middle of the room comes a voice. 40,000. I said, your entire class. He said, no, one method. I mean, this is voice coming from the dark. I said, where do you work? In hell? And I finished my talk, and this developer walks over. And I'm telling you, I could see it in his eyes. He was not telling anything that was wrong. He was dealing with a method which is 40 lines long. He came to me and said, I'm the guy up there who said 40,000. I said, brother, what happened? He said, no, it's worse than that. So what is worse? I got hired specifically to refactor that method. I said, you could have called one of us who would have told you don't do this. So this was November 2015. I was speaking there November 2016, and he shows up. He comes to me and he says, do you remember me? I said, how could I forget you? He says, I don't know why this is happening, but I have this feeling in me that I have to come and share my status update with you, if you don't mind. I said, I'm all for it. Tell me what's going on. He said, well, a year ago, you had 40,000 lines. Yes, 40,000 lines, but it's been a year now, and I've been working on this code. I said, so what's the status? We're down to 30,000 lines now. So both of us agreed we'll meet again in November 2017 with the hope it'll be down to 20,000 lines now. Well, it's kind of scary when you have these kinds of methods. I was speaking to a developer in Boston a few weeks ago, and he said, I got something better for you. I said, yeah, what is it? He said, 60,200 lines. I'm like, why that number? He said, because we hit a compiler limit. There is hope. There is definitely hope after all. So we can agree that long methods are a bad idea. We talked about some of the reasons. But how long is really long? If I tell you 1,000 lines is long, who would agree? Okay, so most people seem to be agreeing in some way or the other. 500, okay, about the same. 100, a little fewer, but mostly. 50, a lot fewer. 25, even, okay, this should be Ruby programmers. What about 7? Okay, Clojure programmers. So the point really is, we can't compete with this, right? Because the number of lines of code is not really clear because we don't agree on it. Well, somebody told me I got a better measure. I said, what is it? And they said, if you can show me the entire function in one window, then it is short enough. And the minute you say it, somebody says, what's your font size? So there is no way to win that too. Well, it turns out it's not really about the length of methods. Sure, length of methods is interesting to look at. But what we really need to focus on is not the length of the method, but the level of abstraction. So it turns out it's what we really are after is not the length, but really the width. So in other words, what is the number of levels of abstraction you are dealing with? So here is an example I'll give you, a rather a crude example to illustrate the point. You know that you have a colleague who is writing long methods. And you've been telling this colleague not to write long methods, but they don't listen. I got one last-ditch effort to convince them. So go on Monday, don't say a word, just sit down and start coding. Your colleague, the one who writes long methods, comes to work and says, oh, you're here already. You say, yep, wait, how was your weekend? You can answer that question in 2 ways. You can say, oh, the weekend was great. I went to the park with the kids on Saturday and went to the movie on Sunday. But don't say like that. Instead, you say, oh, the weekend. Well, exactly at 7 o'clock, I got into the car, put the car in reverse, took the car out, took a left turn, drove for 2 kilometers, took a right turn, and then drove for 7 kilometers, took a roundabout. I missed the roundabout, went around it 2 times. The kids loved it. And then I took the first exit out of it, went 3 kilometers, and took a right turn. There was a beautiful bird on the tree in that case. Just keep going like this. At some point, your colleague will say, have you gone mad? You say, no, I've not gone mad. I thought I'll tell you how the weekend was, like the way you write code. And the point really is, we don't communicate that way with people when we talk to them. Instead, we give them knowledge chunks. I went to the park on Saturday, went to the movie on Sunday. Your colleague may say, oh, really? Which park did you go to? Notice they didn't talk about the movie, they talked about the park. Oh, the park by the main street. Oh, yeah, I've heard about it. Is it family friendly? Oh, of course, I took the kids with me. What kind of activities do they have? Notice we are drilling down deeper and deeper into this abstraction related to the park facility, not about the movie. Exactly the point when it comes to how we communicate in code. So when a function is dealing with a single level of abstraction, I went to the park on Saturday, movies on Sunday, that's one level of abstraction, not telling anything more about the park or the movie at this point. Then when we come back, of course, we can talk about the movie or the park separately. So it's a level of abstraction that makes a big difference, and it's a level of abstraction that really corresponds to cohesion as well. And the more levels of abstraction we have to deal with in a piece of code, the harder it really becomes. The next thing I want to talk about is give meaningful names to things. Variables, classes, methods. I'm going to say this is not easy. A programmer, one who can name their children quite easily, but has a very hard time naming their variables. I remember very well, as I'm struggling to write variables, my wonderful wife came to me and said, we're going to have a baby. I said, awesome. I want a name for the baby. Here's the name. She's like, wow, that quickly. Absolutely. That's the name. Yes, we have decided that's the name for the baby. Do you want to think about it? I said, sweetie, this is the name for the baby. Now, if you'll allow me, I got to think about the name for my variable. It's really hard. And it takes a lot of effort to come up with names for variables. And when you do, the next colleague of yours says, I don't like this variable. So it takes a lot of effort, but it's important to take the time to really find these variables. I came across this code at work. I had a company I was working with, and I kindly asked them, do you please allow me to take a photo of this? And they kindly said, yeah, go ahead and take a photo. And so I took, and I'm so happy I did. Oh, I'm sorry, I didn't want to really take a photo of this. What I really want to take a photo of what was below this. It said, God help me, I have no idea what this means. This is a piece of code that the programmers have to maintain, and they have no clue what these variables mean. Can you imagine going to work when you have to deal with code where all these variables are cryptic? I got two theories about this. The first is, we don't work in software development. We work in what's called software archaeology, because you go to work to discover what the code actually meant. I remember going through a cave, and in the cave they had a little board, a little description next to an artifact, and they said this artifact had meaning to the creators long time ago, but over the history that meaning is lost forever. And when I read it, I screamed, I said, oh my gosh, nothing has changed, because this is what I do at work every day. Because I go to the work and say, this code had a business meaning once upon a time. When the developers walked away, the meaning was lost forever. And this is something, so it's a software archaeology we work with. The other thing I actually am beginning to realize is, the other day I was looking at a piece of code, reviewing it. The variable names were absolutely random. I quit reading the code. I was trying to find a pattern among the randomness. I'm like, this is K, this is Z, this is W. What would the next variable be? And then I realized programmers actually don't name their variables anymore. Seriously, I think this is what is happening. I'm sure Simon will appreciate this really well. So as you're coding, your cat walks over the keyboard. And you take your cat and say, oh, little cat, wonderful. You wrote variable names for me today. There you go, thank you. And then you continue to code after that. I mean, humans cannot have, would you agree? Absolutely. So it's all cat-created variable names. Humans don't create this. That's why they are so cute as well. So, but problem with this is, variable names represent abstractions. If we don't give good names for variables, what happens? Well, we lost the abstraction in the process. So if we cannot name a variable or a function appropriately, it might actually be a sign that we have not yet understood its true purpose. So trying to take the time to understand so we can give a good name to it becomes a lot more easier to work with. I'm a huge fan of code reviews. When I mention code reviews, often people don't like it. But one of the reasons is people do code reviews really bad. For example, in some companies what they do, well, I'll tell two practices that are really pretty bad, I think. The first practice is they bring the entire team into a room and they start doing code reviews. That's a terrible approach. You go to the boss and say, oh, next Thursday we're going to have code review. The boss freaks out. And the boss says, wait. It's kind of like what you did 3 months ago when on a Thursday you brought everybody into the room, projected the code on the screen, and you started critiquing. Oh, yes. Heck no. Because the last time you did that, there was a fight. We had to call the cops and 2 people quit. No more code reviews for you, right? So we don't like such code reviews. It becomes really, really hard. The other practice I think is really silly is where companies say you cannot check in code until you finish the code review. Really bad idea. Because what I've seen people do in this case is they haven't checked in code. Why? Because somebody else has not reviewed it. And because you've not checked in code, everybody is waiting. And one day they come to you and say, we got to go to production. Where's the code? Waiting for code review. Don't worry about it. Hey, review it now. It looks good. We're done, right? So that's not very effective either. Code review works really well when the people on the team have realized the benefit for it. If I am convinced that you reviewing my code is going to make my code better and make me better, I'm going to ask you to review my code. In that regard, keep in mind that code reviews are both technical and sociological. Never say anything negative in the code review. Here are some really bad examples of code review. This code sucks. What were you thinking when you designed this? Were you on drugs when you wrote this? Things like that are really bad things to say. Or you can keep going, escalating it. I always suggest, don't tell me what's broken when you do a code review. Instead, tell me what can be done better. When you tell me what can be better, you give me two options. I can do that, or I can come back with something even better than what you suggested. But instead, if you tell me, this code sucks, I'm left with, I know I did something silly, but I don't know what really is silly. I might be thinking of something different from what you really thought, and I don't even know what are some of the options to fix it. So always show people how to write better code rather than telling them the code is bad. This is one of the reasons why I love automated tests. Oh, by the way, not only do I review code, but I start reviewing tests first. That's also one way to make sure that people have written tests also. So we review the test, and then we review the code after that. And of course, when you are reviewing this, there's another thing I've started doing about maybe 5-6 years ago. I can't remember exactly when I started doing it, but I remember when what I started doing. And it's a little bit more effort. It's not easy, but I think this is a better way. What I used to do when I did code reviews before, when I find a bug, I would tell there's a bug. Maybe I'll write a little comment explaining what the bug is. And then one day I realized, hey, wait, rather than writing what the bug is, I can actually write a test that fails because of the bug. It took me about 15 minutes to do it. But when I did, I quietly checked in my test saying nothing. The continuous integration failed. And I'm okay with that, actually. The developer who wrote the code got a little notification saying, Venkat checked in the code and your code now is not working. About an hour later, I get an email from this developer saying, aha, I see what you did there. You wrote a test because you found a bug, but did you know there were 3 more bugs than what you found? So I wrote 3 more tests. I'm like, yes, that's exactly what we want to do. So when you find a bug, don't fix it. Write a test and then fix it. And by writing a test rather than explaining what the bug is, you're promoting that kind of behavior. And even better, about 3 months ago, I found a bug. I started writing a test for it. And no matter how hard I tried, I couldn't write a test that fails because of the bug. And that's when I understood it was not a bug. It's just that I didn't understand the code properly. And so I had to refactor the code to make it better, and that can be very helpful also. So talking about this, we call this tactical code review. So what is tactical code review? Well, I write a piece of code. I ask him to review the code. The next piece of code I write, I ask her to review the code, and we rotate the code who reviews the code. In the meantime, when she's reviewing my code, somebody else could be reviewing her code that she wrote, and we rotate among the developers. We don't bring the team together and do it. Of course, if you're doing pair programming, it can be an instantaneous code review right there as well. The last thing I want to mention quickly here is reduce state and state mutation. If you ask me if there's one thing I do today that I'm doing very different than I've been doing for the past 10 years, I would say I'm becoming very sensitive to state. When I work with developers, one thing I notice quite often is people pollute classes with more state than necessary. Minimalism, trying to remove and minimize state, has been really a learning experience for me. Think more, type less, aim for minimalism, fewer state, less mutability, and just enough code to know the relevant parts of a problem. I'm going to kind of be a little sentimental here and say, messing with the state is the root of many problems, both in software and in politics. And by staying out of somebody else's state, it's a much better thing to do, right? The world can live in more harmony when we do this. And so reducing state and not messing with state is a good thing. Mutability often needs company, and it's often found in the company of bugs. And we see this also, the more the mutability is, the more bugs are usually in the code as well. And so we talked about the 12 ways to make the code suck less. So here's the rundown of the list. Schedule time to pay technical debt and also includes slack time. Favor high cohesion and low coupling and eliminate coupling as much as you can. Program with intention. Avoid primitive obsession. Prefer clear code over clever code. Apply the Zinsser principles on writing to coding. Comment why and not what. Avoid long methods. Apply the SLAP principle, which stands for single level of abstraction, rather than having multiple levels of abstraction. And give code meaningful names, because they do represent abstractions. Do tactical code reviews where you rotate the review and do it continuously, and not being mandated by process, but by desire to really review the code and the benefit that it provides. And reduce the state and state mutation. Just to leave some closing thoughts, if you ask me if there is some learning that I've had over the years, since the time I started writing code, when I started writing code, I thought my job was to write code. And I would write code, but over the time I realized writing code is just a small part. Code is never written, code is always rewritten. So I'm going to leave with this thought. The first step in becoming a better programmer is to let go of the conviction that we can code it once and get it right on the first write. I think we should really write it quickly so that we can start rewriting it, improving it, refactoring it. Because we're not going to write code once, we're going to rewrite it many times, and we're going to read it many, many times as well. Hope that was useful. Thank you.